You're sitting in a chair right now. You feel it, the weight, the pressure, solid, real, undeniable. Hit the table. Hear the sound. Feel the pain. But what if I told you that table never touched you? Not once. Not for a single instant. The atoms in your hand and the atoms in the table have never made contact. Physical contact between atoms is impossible. What you call solid, what you call touch, is an invisible force shield. Electromagnetic repulsion, a ghost pushing back. Real, but not what you think it is. I'm Richard Feynman, and I want to show you something that will permanently change how you experience the physical world. Not metaphor, not philosophy. Physics. Tested. Confirmed. True. The chair holding you up right now is mostly empty space, and the part that isn't empty space, the part you think is solid, is a field of force. Invisible. Electromagnetic. Keeping your atoms from falling through the floor not by blocking them, but by repelling them. You are floating. Right now. A fraction of a nanometer above everything you think you're touching. Bear with me, because this requires starting with what an atom actually is. You learned atoms in school. Nucleus in the middle. Electrons orbiting like planets. Tiny solar system. Compact. Solid, like a little marble. Wrong. Completely wrong. Not even close. Here's the real picture, and I want you to sit with this for a moment. If I took a hydrogen atom, the simplest atom, one proton, one electron, and expanded the nucleus to the size of a marble, you know how big the atom would be. A marble sitting in the center of a stadium. The electron somewhere in the bleachers. Occasionally. Probably. Everything between the marble and the bleachers? Nothing. Empty space. The atom is not a tiny solid ball. The atom is almost entirely nothing. A vast, echoing emptiness with a tiny, dense nucleus at the center and an electron cloud so diffuse it barely qualifies as matter. You are made of these. Trillions of them, packed together, making up your hand, your bones, your brain, but mostly empty space, almost entirely empty space. If you removed all the empty space from every atom in the human body, compressed every nucleus, every electron cloud to touch, the entire human race would fit in a sugar cube. So why don't we fall through the floor? This is the question. And the answer is the most important thing I'll tell you today. Imagine two magnets, same pole facing each other, north to north. Push them together. You feel resistance, a cushion, something pushing back. But look between the magnets, there's nothing there. No wall, no barrier, just air, just space. And yet you can't push them together. The force is real, the resistance is real, but there's nothing there to resist with. That's what's happening between your atoms and the floor's atoms. Right now, constantly, invisibly. The electrons in your atoms, that diffuse cloud buzzing around each nucleus, carry negative charge. The electrons in the floor's atoms also carry negative charge. When they get close to each other, they repel, like charges repel. Electromagnetic force. That repulsion is what you call solid. That repulsion is what you call touch. That repulsion is what hurts when you hit the table. Not contact. Never contact. Force at a distance. Invisible. Electromagnetic. Let me make this concrete. Let me give you the actual numbers. The distance at which atomic repulsion becomes strong enough to feel like solid contact, the distance at which atoms touch in any practical sense, is about 1 angstrom, 1/10,000,000th of a meter. At that distance, the electromagnetic repulsion between electron clouds becomes so strong it feels like a wall. But the atoms themselves, the nuclei, are still 100,000 times smaller than that. The nuclei never come close to each other. You hit the table. Your hand stops. You feel pain. Your nerves register impact. But your atoms and the table's atoms are separated by a distance 100,000 times larger than the nuclei themselves. In atomic terms, they're not even in the same neighborhood. The table stopped your hand with a force field, not a surface. A field. I remember explaining this to a student, graduate level, smart kid. He'd been doing quantum mechanics for 2 years, knew the mathematics perfectly. I asked him, when you sit in a chair, what's holding you up? He said, the chair. What part of the chair? The surface. The material. What's the material made of? Atoms. What are the atoms made of? He paused. He knew the answer. Nucleus and electrons. Mostly empty space. So what's actually holding you up? I asked again. He sat there quietly, working through it. I could see the moment it landed. The electromagnetic field, he said. Right. The chair isn't touching you. The chair's electromagnetic field is touching your electromagnetic field. You are being held up by invisible force, like a magnet, just smaller, just faster. He looked down at his chair, actually looked at it, like he'd never seen it before. That's terrifying, he said. That's physics, I said. But here's where it gets even stranger. Bear with me again, because there's a second layer to this, and it's deeper than the electromagnetic repulsion. There's something called the Pauli exclusion principle, named after Wolfgang Pauli, one of the strangest, most powerful rules in all of quantum mechanics. It says no two electrons can occupy the same quantum state in the same location. Simple statement, profound consequence. When the electrons in your hand try to get close to the electrons in the table, when they start to overlap to share space, the Pauli exclusion principle forbids it. The electrons cannot be in the same place with the same quantum numbers. It's not allowed, not by a force, by the mathematics of the universe itself. The electrons resist, not because they're repelling electromagnetically, though they do that too, but because existence itself forbids two electrons from occupying the same state. This is called degeneracy pressure. It's what holds white dwarf stars up against gravity. It's what keeps the floor solid under your feet, not material, not contact, mathematical law. Let me tell you what this means for stars, because it shows how real and how powerful this principle is. When a star like our sun runs out of fuel, it collapses. Gravity wins. The outer layers fall inward. The star shrinks. But it doesn't collapse forever. At a certain point, the electrons in the star's core get packed so tightly that the Pauli exclusion principle kicks in. The electrons refuse to share space. They push back, not with a force, with mathematics, with the law that says two electrons cannot occupy the same quantum state. This resistance degeneracy pressure is strong enough to stop the collapse of an entire star. A star, hundreds of thousands of times the mass of the Earth, held up not by heat, not by energy, but by a mathematical rule about what electrons are allowed to do. We call this a white dwarf, a dead star, supported forever by the same principle that keeps your feet from sinking through the floor. The floor under your feet is the same physics as a dying star, the same mathematical law, operating at wildly different scales, producing the same result: resistance to compression, the sensation of solid, the inability to pass through what is almost entirely empty space. The floor is solid because the same rule that supports dead stars says it must be. The floor is solid because existence itself requires it. The floor is solid because the laws of quantum mechanics prohibit its electrons from sharing space with your electrons. Full stop. Think about what that means. The solidity you feel, the hardness of the table, the firmness of the ground, the resistance of the wall, is not material. It's legal. It's a consequence of a mathematical rule that says certain quantum states cannot be duplicated. You are not sitting on matter. You are sitting on mathematics. Now let me address the objection, because I know what you're thinking. You're thinking, but it feels solid. When I hit the table, it feels like contact. It hurts like contact. If it's just a force field, why does it feel like hitting something? Because your body evolved on the surface of a planet full of atoms. Your nerve endings evolved to detect electromagnetic repulsion between electron clouds. They didn't need to know what was actually happening. They just needed to report it accurately. When the electromagnetic repulsion between your hand's electrons and the table's electrons exceeds a certain threshold, your nerves fire. Your brain interprets this as solid, contact, hard surface. The interpretation is perfect. The reporting is accurate. The sensation is completely real. But what's being reported is not what you think. The solid you feel is a field. The contact you experience is repulsion. The hardness is mathematics. Your senses are not lying to you. They're just not telling you the whole story. This is like being a blind person reading Braille. The fingertips feel bumps. The brain constructs meaning. The meaning is accurate. It correctly represents the words on the page. But the fingertips aren't reading letters. They're reading pressure patterns. The letters exist at a different level than the sensation. The solidity of the table exists at a different level than the sensation of solid. The sensation is real. The electrons never touched. Now let me push this further. Because once you accept that solid is electromagnetic repulsion, you start seeing it everywhere, in things you'd never expect. MRI machines. You lie inside a massive magnet. The field is so strong, a metal chair left in the room would fly across and punch through the wall. But you feel nothing. The field passes through you completely. Why? Because you are mostly empty space. The field has almost nothing to interact with. Your atoms are so far apart relative to their own size that the magnetic field flows through the gaps. But here's the catch. Inside that mostly empty space, The MRI is doing something extraordinary. It's flipping the spin of hydrogen nuclei in the water molecules in your body, using the quantum properties of those nuclei, mapping their location, building an image of your organs, your brain, your tumors, your health. It's reaching through the emptiness of your atoms to manipulate the tiny dense centers. The solid you feel is irrelevant to the MRI. It passes straight through, because the solid you feel isn't really there. It's a field effect at the surface. Inside your open space. And consider neutron stars. When a star collapses beyond the white dwarf stage, when even electron degeneracy pressure can't hold it up, the electrons and protons are forced together. They combine into neutrons. Now you have neutron degeneracy pressure, the same Pauli principle, but for neutrons. A neutron star is about 20 kilometers across, but it contains more mass than our sun. A teaspoon of neutron star material would weigh 1 billion tons. Why is it that dense? Because neutrons can be packed much closer than atoms before the exclusion principle kicks in. The empty space that makes up most of ordinary matter is gone. The electrons are gone. What's left is neutron against neutron, held apart only by the mathematical rule against shared quantum states. A neutron star is what matter looks like when you remove the illusion of solid. It's what's left when the electromagnetic force fields that create the sensation of contact can no longer hold the structure open. It weighs 1 billion tons per teaspoon, and it's still not touching itself. Still fields, still mathematics, still the exclusion principle doing its invisible work. You are made of the same stuff, just with more empty space between the parts. I want to take this one step further, because this isn't just a curiosity about tables and chairs. This changes what matter is. For 2,000 years, since Democritus, since the ancient Greeks, we imagined matter as stuff, tiny, hard, indivisible pieces of stuff, atoms as little billiard balls, solid at the bottom. But there is no solid at the bottom. All the way down, it's fields, forces, mathematics, probability distributions of electrons, quarks held together by gluons, which are themselves field particles. Everything interacting through forces carried by particles, which are themselves excitations of quantum fields. I remember the first time this really landed for me, not as an equation, as a physical fact. I was eating lunch, Caltech cafeteria, holding a sandwich, and I stopped mid-bite because I suddenly realized my fingers are not touching this bread. The electron clouds of my fingers are repelling the electron clouds of the bread's surface. I am holding it with invisible force. I am holding it with electromagnetism. The sandwich didn't care. It stayed in my hand. It tasted fine. But I sat there for probably 5 minutes just holding it, thinking about what was actually happening between my skin and the crust. The billions of atomic-scale force interactions producing the unified sensation of grip, of contact, of solid bread in a hand. My colleagues must have thought I'd gone strange. Maybe I had. Maybe that's what physics does to you eventually. You hold a sandwich and see the quantum fields. But I think that's the right response, not to be paralyzed by it, not to stop trusting your senses, just to know more than your senses tell you, to feel the solid and also know what solid is. Solid is not a property of matter. Solid is what fields feel like when they interact strongly enough to resist each other. When you hit the table, you're not hitting matter. Two fields of force are meeting, resisting, responding, the universe enforcing its mathematical rules about which quantum states can coexist. And it hurts, because your body evolved to take that seriously. This is the thing I find most astonishing about physics, not the equations, not the predictions. The fact that everyday experience, the table, the chair, the floor, the weight in your hand, turns out to be something completely different from what it appears to be. And yet it works. The table still holds the coffee cup. The floor still holds your weight. The pain in your hand when you punch a wall is completely accurate information about a completely real physical process. The universe is not lying to you. It's just more interesting than you thought. Democritus imagined atoms as tiny solid spheres. He was wrong about the solid, but he was right that there's a level at which things are simple. The level isn't solid matter. The level is mathematical law, quantum rules, field interactions. At the bottom, the universe is not made of stuff. It's made of rules. And those rules interacting with each other across the quantum fields that fill all of space produce the sensation of solid, the resistance of matter, the pain of impact, the feeling of a chair supporting your weight. All of it real, none of it what it appears to be. The chair is holding you up right now, absolutely, reliably, the same way it always has. But it's doing it with a ghost, an invisible electromagnetic field, a mathematical prohibition against shared quantum states. You are floating above everything you've ever touched, a fraction of a nanometer above the world, held up not by contact, but by force, not by matter, but by law. And you've felt this your entire life without knowing it. That's not a failure. That's what it means to be a large creature made of atoms, living in a world of atoms, with senses tuned to the scale where all the interesting interactions happen. You feel the field. You call it solid. You're not wrong. You're just missing the mechanism. And now you have it. The table never touched you. It never will. And it will hold your coffee cup just as reliably as it always has. That's physics. That's the world. More strange and more trustworthy than it has any right to be. Welcome to the real texture of reality. Force where you expected matter. Mathematics where you expected substance. And a universe that somehow produces the sensation of solid from something that was never solid at all. That's what's under your hands right now. That's what's under your feet. And it's holding you up perfectly. It always has. It always will. Just not the way you thought.